and welcome back. Today we are going to be measuring the density of a baked bean can. Like I said before, it really doesn't matter if you don't have a can of baked beans. We're literally just doing this for the practice of mixing together lots of different measurements. So just any can, any 400ml can will do. 400ml is right? Yeah. Around that, 400 gram, whatever this can size is. Anything will do. Okay, if you don't have a big one of the squat ones, you would get slightly different numbers, but it's really not going to matter. The process will be exactly the same, so you will be absolutely fine, hopefully be able to understand what's going on. In this first video, I'm just going to set you up to send you on your way to do your measurements and your calculations. I'd really like you to try to do as much of this process on your own as possible. So really try and just start with me. The video will end, you'll go off and finish the measurements, finish your calculations, calculate all your uncertainties, get a final value, and then you can watch my tutorial video on how I did it, and then you can kind of fast forward through it if you're pretty confident and see if our final values come out pretty much the same. Obviously, they're not going to be identical. You and I are going to make slightly different measurements, but what we're looking for is the measurements being roughly in line with each other and the uncertainties being roughly in line with each other, okay? And really essential is the process is pretty much the same. You also want to watch out when you do see me doing mine, looking at how I lay things out. Now, I know us as physicists, we tend not to always be the neatest of workers, and neatness is not important in sake of itself, but it is important when your calculations get longer and longer, then it is important to be able to accurately keep track of your logic, okay, and see things progress forward. So laying out a calculation of this size, it is important to pay attention to how you're setting things out, where you're setting your data, and making sure that, for example, every single calculation comes with a formula first. We're not just putting random numbers down, we're certainly not putting them down at weird angles without units. So let's pay attention to that. So even if you're very, very confident when you are looking at my tutorial video after that you've done the right thing, you perhaps want to then give yourself a little bit of critique of, well, have I really shown this as clearly as I can? Because we mustn't lose sight of what we are trying to do as physicists. We are not simply trying to calculate a number. That is not the point of what we're doing. Our job is to try and understand the universe and explain it to the rest of humanity. Okay, that's our job. And so simply knowing in yourself that you can get to the right final number, that's not really achieving as a physicist. You need to be able to show other people how to get to that number. That's being a scientist, okay? To show how you got there and being transparent. And one of the ways you're being transparent in your scientific process is by clearly showing your logic and your steps. So don't see showing your steps as a kind of a sort of failure. I know some of my students sometimes interpret it as, well, if the more steps I show, the less I've been able to do in my head. That's really not a kind of badge of honor in physics. We are trying to explain how to get things. We are trying to be transparent. We are, the whole purpose of uncertainties is to demonstrate just how fallible we are. So let's pay attention to our layout after that big long speech. Okay. So my can of beans, let's start our notes together. As you should have been doing all the way through this series, when I make a note, you make a note. Okay, so my title's going to be off to the right. That's really frustrating. Density of a can of baked beans. My writing got worse and worse as I went over to the side there. Okay, so some of the basics. What we have here is a cylinder, okay? So we've basically got a circle that extends down for some height. Okay. The circle has a cross-sectional area here, and then we have a height here. And so that area times that height, that would give our three-dimensional volume. So density is equal to mass over volume. And as advanced hires now, folks, really should be paying attention to how we write our symbols. The symbol for density is the Greek letter rho. It is not a P. Okay, start from the bottom and curve up. So density is equal to mass over volume. So those are the two measurements we're going to need to make. For our mass, we're simply going to sit our bean can on a set of scales. Anything you can get a hold of will be fine. So for our mass measurement, we're going to get a mass that will state in kilograms. We'll have a delta R, a reading uncertainty for that. And, you know, we're going to pop in a delta C. Now, try and find it. I doubt you'll be able to. I doubt that most kitchen scales publish themselves with a calibration uncertainty. So you know what? If you can't find one, let's just use our standard kind of hardest version of a calibration uncertainty so that we keep practice using it. Okay, so our calibration uncertainty for our balance, if you can't find it, is going to be plus or minus 0.5% of the reading plus one digit. Because I always think that form of calibration uncertainty needs practice. So we'll just take that as our standard calibration uncertainty here. Okay, so there's how we do our maths. You can set your page up like that right now and just fill in those numbers when you go and get them. Now, I'm about to kind of go a bit deeper into how we're going to do the volume and show you my first data table. No measurements, I'm just going to go down to the first data table. If you do not want this assistance, just pause now or stop the video now and go and do your experiment. If you would like to do this with as little assistance as possible, stop now, go and do it. If you'd like a little bit more help, particularly with your layout and perhaps how you're going to do your first data table, then stick with me for another few minutes. So volume. So our volume is simply our area of our circle times height. Okay, our area is of course taking care of that kind of breadth times width issue, but here we've got a circle, so it's actually going to be the area of a circle. So that is going to be pi times pi r squared times height. Now, we're not as a raw data measurement going to be able to take r. It would be pretty tough to find the halfway point and unnecessary. So let's split that into pi times the diameter over 2 squared times height. Okay, and now we've got a couple of constants hanging out here. We've got a pi and a 2, so let's take them out the front. Okay, so that's pi over, now remember that's over 2 squared, so that's pi over 4 d squared times height. Okay, and that is the formula we're going to be putting numbers into to get our volume. So you can see now, guys, that we're practicing all sorts of stuff. We've got a power, we've got multiplying things, we've then got a separate calculation. We're going to do multiplication here, which is going to require that combining formula, and then we'll be doing finally a division, which requires that combining formula again. Okay, so let's set up our table to collect our diameter. Now, when we measure our diameter, guys, we are going to repeat that measurement. And the way you repeat a measurement like this, where it seemingly doesn't change, is you do the measurement and then you change your axis. And you do the measurement again and then you change your axis. Okay, just like that. And it's the same with the height, guys. You'll measure the height, then you'll rotate your can, you measure height. You won't do it like that, like a floating measurement. You'll do it like this. Okay, so let's all try and agree on what we're actually going to be measuring here. So for the can itself, obviously the top of the can is a seal that gets broken, but I believe the beams of the can are really kind of going to the, to the edge on the inside. So I'm going to measure my diameter from inside edge to inside edge. These right outer edges here. Okay, so from inside edge here to inside edge here. Okay, so I'm going to ignore all the kind of seals of the top and everything like that. In terms of my height, I'm going to measure from kind of seal to seal, so the top of the lip here to the bottom of the lip there. Okay, that's what I'm going to measure my my height as. Might not be perfect, but that's what I'm going to do. So if you want to be consistent with me and have pretty much the same numbers, that's what I'm going to do. So the first thing I'm going to measure is my diameter. So I'll pop a kind of heading for my diameter. I'm going to be measuring it in meters, but when I actually read it off my ruler, I'm going to number it in millimeters. So I'm going to use my units as times 10 to the minus 3 meters. And that just allows me to keep all those decimal places out of my data boxes, which is really helpful. We then want to pop on a reading uncertainty. Now, I've got my ruler here, so I know my standard reading uncertainty of a ruler is 0.5 millimeter. It might be when you're carrying out a measurement, and this is more common in advanced higher than higher, it might be that when you're carrying out a measurement, you think, you know, I really don't think I can be as precise as 0.5 millimeter here, okay? So if you feel while you're carrying out an experiment that as you're carrying it out, you realise the measurement is really quite hard to take. It's hard to be precise with, it's hard to really know where to go, which number to take. You can always increase your reading uncertainty, always. Reading uncertainty is at the scientist's discretion. So I'm going to pop 0.5 millimeter down here, but it may be that in the course of my experiment, I increase it, okay? But just so I don't forget about my reading uncertainty, just so there's one there, I'm going to pop 0.5 times 10 to the minus 3 millimeter. Okay, but never be, your reading uncertainty should account for all issues you feel are there in taking that reading. So it should be as large as you think it needs to be to account for any problems you are in taking the reading. Because the reading you're basically saying, I guarantee, absolutely guarantee, that this reading is inside the boundary of my uncertainty. So if my uncertainty is just 0.5 millimeter, if I'm saying that, say my reading is 10 millimeters, I'm saying it absolutely was not less than 9.5 and it absolutely wasn't bigger than 10.5. There's no way it was outside of that arena. And often we just cannot be that precise. So we're going to do it 5 times, because that is the advanced higher SQA minimum. We actually often, in practical terms, when we're doing our assignment, often do 6 repeats just to kind of overdo that, basically. But I'm going to do 5 today just because it's the standard SQA minimum. And I'm going to have a mean. I'm going to have a random uncertainty. I'll have a calibration uncertainty, which you can go and look up, guys, in our calibration uncertainty sheet, which will be attached again in the description of this video. I'm then going to have an overall uncertainty in my diameter, and then finally in my diameter. Now I'm running out of space here. What I'd actually like to have in my, I really spread out my numbers here too much, didn't I? They were way too spread out. What you can also have in your table, guys, so another 2 columns, a column for d squared and a column for delta d squared. I'm probably just going to do them underneath here, but you can absolutely have those in columns of your table. And I would always recommend having things in your table as much as possible. Okay, so it's like a one-stop shop for people to find your data. And also it makes it really easy for the marker or whoever's looking at your data to see that your significant figures are being consistent and give you those marks really, really easily. Okay, so I'm going to stop at this point. I'm going to stop this video and you are going to do your very best to go and find the density of a can of beans. Okay, so you're going to find your diameter, you're going to square it, you're going to find the uncertainty in that square, then you're going to times it by your height. Your height will need another table just like this, okay? You're just going to do it step by step. Remember, you do the measurement, all of your raw measurement calculations, then you do the calculation, so you do the multiplication, then you take care of the combining uncertainty for that calculation. So calculation first, followed by uncertainty. Measurement first, followed by uncertainty. So measurements, followed by all uncertainties. Then calculation, followed by all uncertainties. Okay, just step by step. I'll see you in the next video to see how we all did. Thanks, folks.